Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to solve logarithmic equations. Alright, so the instructions for the example that we're going to be working on are as follows. We are to solve the given logarithmic equations. We're going to solve them algebraically. Okay? Alright, so for question 1, let's say we have the log equation log base 2 of x equals -5. Alright, so the solution is as follows. To solve, of course, involves isolating the x. So log base 2 of x equals -5. Now, to get rid of this log, we're going to use the inverse of log. Okay, the inverse of log base 2 is exponent base 2. Alright, so the inverses of logs are exponents. So since the base of this logarithm is 2, we're going to exponentiate both sides of the equation using 2 as the base of our exponentiation. Okay, so what does that look like? We put a big 2 on the left and a big 2 on the right. Alright, and then on the left side we'll have a little log base 2 of x equals 2 to a little 5. Alright, so this is what exponentiating both sides with a base of 2 looks like. Now, why are we doing this? Well, it is because if you have an exponent of a certain base raised to a log with the same base, we have an inverse of the composition of two inverse operations. Alright, so what happens when you compose two inverse operations? They cancel each other out. So this 2 and this log base 2 are gone, and all you're left with is the logarithmic argument, which is x. Okay, so that x comes down. On the left side, we are going to have x equals 2 raised to the -5. Alright, so what we just used on the left side is the inverse property of logarithms. So don't forget, to get rid of logs, you use exponent with the base of your log. Okay? Alright, let's simplify the right side. We can use the reciprocal property of exponents to write this as 1 over 2 to the 5th. Remember, anytime you reciprocate, you negate the exponent of the number that you reciprocated. And then we can expand that. This gives us 1 over 2 to the 5th is 32. Alright, so does this answer satisfy the domain restrictions for this problem? The restrictions are as follows, because we know that there are restrictions on the domain of log. So the restrictions for this particular problem is that the logarithmic argument, namely x, has to be greater than 0. You can't find the log of 0 or anything less, only things that are greater than 0. Okay, so since this is a restriction right here, our answer 1 over 32 is greater than 0, so it meets the restriction. Hence, we have a valid solution, a solution that does not violate the domain restrictions of the original problem. Okay, so remember to always check for the feasibility of your solutions when you're solving logarithmic equations, because sometimes extraneous solutions can be present, and those have to be identified and eliminated from the solution set. Okay, let's take a look at another example. Let's say we want to solve the equation natural log of 3x equals 5.1. Okay, alright, so the goal here is to get x isolated. So we have the natural log of 3x equals 5.1. Now, what is the base of the natural logarithm function? There is no base specified, but it does have a base. It's a visible base, just like the common log has a base of 10. The natural log has a base of e, the natural base. Okay? To get rid of log, we're going to use the inverse operation, which is exponent. Since the base of this log is e, we're going to exponentiate using e as the basis of our exponentiation. Alright, so we're going to put, just like we did in number 1, a big E on the left and a big E on the right. And on the left side, we're going to have a little natural log of 3x, okay, equals e to the 5.1. On the left side, e and ln, which is log base e, are inverses. So what happens? Those two cancel each other out, and we're left with the logarithmic argument, which is 3x. So we'll bring that down, and we are left with 3x equals e to the 5.1. Okay, remember e is an irrational number, just like pi is 2.7, and it's a non-repeating, non-terminating decimal. Okay. All right. Now to finish this off, we just divide both sides by 3. So divide by 3, divide by 3, and your final answer, x, is going to be e to the 5.1 over 3. Now, does this solution violate the domain constraints here? So let's consider the restrictions. What are the restrictions on this particular problem? You take the logarithmic argument, namely 3x. Okay, you just take the logarithmic argument right there, and the requirement is that whatever you plug in into the log function has to be greater than 0. So 3x has to be greater than 0. Let's solve that. So divide both sides by 3, and then we have x is greater than 0. This value right here, e, is a positive number, so when you raise a positive number to an exponential value, you're always guaranteed to have a positive number. So when you divide two positive numbers, you are going to have a positive number. So this solution that we have here, you can think about it as 2 to the 5th over 3, is a positive number. It does not violate the restrictions on the domain, hence it is a valid solution. Alrighty, so there you have it. Alright, let's take a look at question 3. Now for question 3, let's say we want to solve the log equation, 4 plus 5 times the natural logarithm of 2x equals 12. Alright, so let's go ahead and solve this log equation. So we have 4 plus 5 ln 2x equals 12. So the goal here is to isolate the term with the logarithmic component and then eliminate the log to isolate the variable. Okay, so first things first, let's move the 4 over to the left side. Subtract 4 from both sides, and that will give us 5. Let's change the color here. 5 times the natural logarithm of 2x is equal to 12 minus 4, which is 8. And then we're going to proceed to divide both sides by 5. Get rid of the coefficient of your log, so divide by 5. Now, you cannot divide by 2x because 2x is the input of the logarithmic function. Okay, so in order to gain access to the 2x, you need to get rid of the log first, alright? So this 5 divides out, and you have the natural logarithm of 2x equals 8 over 5. Okay, so now how do you get rid of log in order to gain access to the 2x and then the x? To get rid of log, we're going to use the inverse of logarithm. Okay, so what is the inverse of logarithm? It's the exponent with the base of the log. So this is ln, so we know the base is e, so we have a big E on both sides of the equation. We're going to exponentiate the equation using e as the base of our exponentiation, since the base of this natural log is e. On the left side, we'll have a little ln 2x equals, on the right side, we'll have a little 8 over 5. On the left side, the e and the ln are inverse functions composed with one another. They cancel each other out, and you're left with the logarithmic arguments 2x. 2x is equal to e to the 8 over 5. Alright? And then to finish this off, we will proceed to divide both sides of the equation by 2. And then finally we have our result, x is equal to e to the 8 over 5 divided by 2. Okay, so there goes your final answer. Alright, so let's first of all ensure that it doesn't violate the domain constraints. In that case, it will be an extraneous solution and we'll have no solutions to this problem. So let's check first and see if it is within the domain boundaries. So what we're going to do is we're going to take the log argument, namely the 2x, okay, what you're plugging into the log function, to determine what the restrictions are. Alright, so domain restrictions are as follows. The log argument 2x has to be greater than 0, since you cannot take the log of 0 or anything less. And then to get x isolated, we'll divide both sides by 2. And then we have x is greater than 0 over 2, which is 0. Okay, so this number right here is 2 to a, if you have a positive number raised to a power, you're always going to have a positive result. So positive over positive is positive. This number is greater than 0, so it's a valid solution and it's not extraneous. Alright, let's take a look at another example. Question number 4, another log equation. Now what if we were to solve, we're asked to solve the equation log base 2 of x plus 3 is equal to log base 2 of 2x minus 1. Okay, so if you look at this problem, we have two restrictions here. So our answer has to respect both restrictions, or the union of the restrictions, in order to be valid. Okay, we'll address that later. Let's solve it first. So log base 2 of x plus 3 is equal to log base 2 of 2x minus 1. We have two logs with identical bases, so we'll just simply exponentiate both sides using the base of our identical exponent. The base of our identical log, sorry, so the base of our logs is 2, so we exponentiating using 2. And then we will have a little log base 2 of x plus 3 equals 2 to the little log base 2 of 2x minus 1. Using the inverse properties of logs, we're going to cancel out 2 and log base 2, and then the same goes on the right side also. So just basically equates the logarithmic arguments. So you can see a shortcut, right? If you have two identical logs, you can just simply cancel out the logs and equate the logarithmic arguments, and you will have a valid argument also. Okay. Alright, so let's go ahead and solve this. We can move the x's to the right, so subtract x from both sides, and then we can move negative 1 to the left, so we add 1 to both sides. Okay, and what's our final answer going to be? Well, it's not our final answer. We're going to have 3 plus 1 is 4. Oh yeah, that's the final answer. X is equal to 4. Or I can just write x is equal to 4. Alright, so does this answer respect the restrictions on the domain? Well, let's see what the restrictions are. So for this one, we have two of them. The first one is x plus 3 has to be greater than 0. Okay, let's solve that. So this requires, the requirement is that x has to be greater than negative 3. Subtract 3 from both sides. And then the other restriction is that 2x minus 1 has to be greater than 0. Add 1 to both sides. 2x has to be greater than 1. And then divide both sides by 2. X has to be greater than 1/2. Okay, so that's a restriction on our domain right here. So what we're looking for is not the union, it's the intersection of these two. Okay, so we're looking for any number that is greater than negative 3 and also greater than 1/2. Okay, so let's visualize that using a number line real quick. So have a number line. We're looking for the intersection of all numbers that are, so let's say this is negative 3, all numbers that are greater than negative 3, and all numbers that are greater than, let's say this is 1/2 right here, and all numbers that are greater than 1/2. If we intersect these two, the intersection of these two, we're going to get all numbers that are greater than 1/2. Okay, so this will actually be your domain. All numbers that are greater than 1/2. Okay, so the answer that we have right here, does it satisfy that requirement? The answer is yes. X is bigger than 4 and 4 is bigger than 1/2. So this is a valid solution. Alrighty. Alright, let's take a look at question number 5. So for number 5, let's say we have to solve log base 5 of quantity x plus 1 raised to the equals 2. Okay, so let's go ahead and solve this equation. So we have log base 5 of x plus 1 equals 2. So we need to get rid of this log using its inverse, which is exponent. So the base is 5, so we're going to put a big 5 on both sides. Exponentiate the equation using 5 as the basis. So we have 5 to the log base 5 of x plus 1 equals 5 to the second power. On the left side, we have the composition of two inverse functions, so they cancel each other out. And we're left with the logarithmic argument, which is x plus 1. X plus 1 is equal to 5 squared, which is 25. To finish this off, we'll just simply subtract 1 from both sides of the equation, and we will end up with our final answer, x equals 24. Now, does this answer respect the domain constraints on this logarithmic equation? Well, let us see. So let's calculate what the restrictions are on the domain. You take the logarithmic argument, which is x plus 1, and it has to be greater than 0. Okay, since you can't take the log of anything 0 or less. Subtract 1 from both sides, and you have x has to be greater than negative 1. Is 24 greater than negative 1? It certainly is, so this is a valid solution. Alright, let's take a look at another example. Problem number 6. Let's say we have the equation natural log of x minus 1 raised to the third power equals 6. How can we solve an equation like this? So natural log of x minus 1 to the third equals 6. The logarithmic argument is x minus 1 to the third. Okay? So we want to get rid of this log so we can gain access to it. So what we're going to do is get rid of the log first. The base of the natural log, we've discussed this before, is e, so we're going to put a big E on both sides of the equation. And then we are going to have to exponentiate these two sides of the equation, okay? So we have a little ln x minus 1 to the third equals e to the a little 6. On the left side, the inverse operations, e composed with ln, will cancel each other out since they're inverses. You bring down the logarithmic argument, x minus 1 to the third is equal to e to the 6th power. Okay, so now to get rid of this power, which is the third power or cube, you do the inverse, which is the cube root, or you raise it to the 1/3 power. Okay, so I'm going to raise this equation, the left side to the 1/3 power. The same applies to the right side, raise it to the 1/3 power. Using the power of a power property of exponents, the left side simply reduces to x minus 1, since 3 times 1/3 is 3. And on the right side, we're going to have e to the 6 over 3. Okay? So we have x minus 1 equals e to the 6 over 3, just divide it by 3. 6 by 3, which is 2. And then you finish this off by adding 1 to both sides of your equation. So your final answer, x is going to be e squared plus 1. Okay, so if you want to approximate what this is, just think about it like 2 squared plus 1 is just like 5. Alright, something bigger than 5. The reason I'm doing that is, does this answer respect the domain restrictions of the original problem? That's the question. The restrictions on the original problem is that the logarithmic argument, so let's figure out what the restrictions are. The logarithmic argument, which is x minus 1 to the third, has to be greater than 0. Okay, so to solve that, we take the cube root of both sides of the equation, or raise it to the 1/3 power. I'm just going to cube root it since the left side is pretty easy. The right side is easy. If you cube root both sides, you're going to have x minus 1 is greater than the cube root of 0 is 0. Add 1 to both sides. X has to be greater than 1 in order for the solution to be valid. So we talked about this number here. It's bigger than 5, so 5 is bigger than 1 for sure. So we know that it is an answer that respects the restrictions on the domain. Alright, let's take a look at another example, question 7. Let's say we have the equation log base 2 of x plus log base 2 of x minus 3. Okay, that equals to 2. We want to solve this. Alright, so this problem looks a little bit weird. It looks different from what we have been doing thus far. What's the difference here? Guys, we have two logarithmic terms on the left side. Okay, so how do we eliminate two logs? Well, it's not possible to do that. What we must do first is we must condense the logs before we eliminate, or consolidate and then eliminate. Okay, to consolidate this, the log expression on the left side, we have to use the product property of logarithms. You just have to remember that the sum of logarithms of the same base is equivalent to the log of the product of the logarithmic arguments. Okay, so the arguments are x and x minus 3. Using the product property of logarithms, this can be rewritten as log base 2 of x times x minus 3. Bam. Okay, the right side stays as 2. Let's simplify the left side. We have log base 2 of x squared minus 3x. Now that we have consolidated our logs to 1, we may proceed with the elimination step. The base of our log is 2, so we're going to put big 2's on both sides. And then we're going to have log base 2 of x squared minus 3x equals 2 to the second power. On the left side, the logs cancel out since they're inverses. We have x squared minus 3x equals 2 squared, which is 4. Subtract 4 from both sides. We have x squared minus 3x minus 4 equals 0. We have a quadratic equation that we can solve by factoring, or the quadratic formula depending on the nature. Put AC on the top, B on the bottom. AC is negative 4, B is negative 3. 1 and 4, let's see what works here. Since the sum is negative, the bigger one has to be negative. So since A is equal to 1, we can skip grouping and jump right to the factored state. X plus 1 times x minus 4 equals 0. Okay, so A equals 1. You skip grouping. You don't have to do grouping when A is 1. Okay. Alright, so using the zero product property, you set both to 0. And then you add, subtract 1 from both sides. This becomes x minus 1 equals negative 1. And this one, x equals 4 when we add 4 to both sides. So do both of these answers, one or neither of them, satisfy the restrictions on the domain of the original problem? Well, let's calculate what the restrictions are and then see which, if any, are extraneous. Alright, so the restrictions, we have two. So first we have x has to be bigger than 0 and x minus 3 has to be greater than 0. Okay, so we're looking for the intersection here. This is already solved, so to solve this we have x has to be greater than 3. Okay, so x has to be greater than 0 and x has to be greater than 3. If you find the intersection of these two, you're going to end up with x is greater than 3. Okay, let me show that to you real quick. So you have, why does my line keeps tilting upwards? Okay, so you have let's say this is 0 right here. Okay, and this is x is greater than 0, and then we want x is greater than 0 and 1 to 3, x is greater than 3. So this 2. When you find the intersection, your answer is going to be x is greater than 3. So this is the interval that satisfies both. Okay? Alright, so the domain restriction on the problem is x is greater than 3. So look at the answers. Do they both satisfy that restriction? The answer is no. This answer right here, x equals -1, is extraneous. Hence, your only answer is +4 because it is greater than 3. Thanks so much for taking the time to watch this presentation. We greatly appreciate it. If you found the contents of this tutorial helpful in your studies of logarithms, do give us a thumbs up. Your positive feedback is very valuable to us. Do not forget to subscribe to our channel for updates to other great tutorials such as this. We upload math tutorials to our YouTube page on a regular basis, so subscribe to get updates. If you have any questions or comments or special requests for math tutorials, just place it in the comment section below and we'll be more than glad to assist you. Don't forget to check out our website at mathgotserved.com for tons of math resources. Thanks again for watching and have a wonderful day. Goodbye.